Hi everybody, my name is Maoxuan Hu. You can also call me Aaron. The paper I am about to share is Taxonomy for the Modeling and Simulation of Emergent Behavior Systems by Olga Thomas, Holland, who is a researcher of US Navy military. When I first seen the title, I was wondering, what is taxonomy? Taxonomy is the science of naming, describing, and classifying organisms and includes all plants, animals, and microorganisms of the world. That is a biological definition. In complex systems, the objectives are emergent behaviors. So, what is emergent behavior? Emergent behavior is the behavior of a system that does not depend on its individual parts, but on their relationships to one another. Emergent behavior cannot be predicted by examination of a system's individual parts. It can only be predicted, managed, or controlled by understanding the parts and their relationships. The key insight of the concept of emergent behavior is the arrangement of the parts, not the parts themselves. That makes the big difference. The chemicals in the human body can be purchased for a few dollars. Buying them and mixing them up in a bucket or even spending 100 years to arrange them would not create a person. That's why it's structure that makes the difference. Emergent Behavior Systems, which is EBS, is the construction of a consistent lexicon of emergent behavior terms and the development of an emergent behavior systems taxonomy. The reason why we need to build the two concepts, which is lexicon and taxonomy, are first, we need to understand what emergent behavior is. Then, establish axiomatic relationships, which is something that is obviously true and therefore not needing to be proved. Then, identify emergent behavior apart from other phenomena. The reason why we need to build the taxonomy for the EBS is that in complexity physics, artificial intelligence, computer science, statics, biology, and social psychology, as well as some other disciplines, are rapidly converging upon a common observation that as analysts and designers further explore their systems of interest, it is becoming clear that the robustness, richness, and diversity observed in both natural and man-made complex systems is more than the simple sum of the components. Depending on the perspective of the observer, there is some level of emergent behaviors. Global at that scale at which interesting and useful behaviors are observed. The establishment of a working taxonomy of emergent behavior systems is critical to identifying the appropriate formalism used to describe them. SCORE in 2001 called for cross-study and joint research in agent-based and system dynamic modeling because the two disciplines almost entirely ignored each other's literature rather than benefiting from one another. Yanir Bar-Yan in 2004 distinguishes between four types of emergence. He gives short description based on particles and in symbols, rather than agents and groups. Fromm and George Chen in 2005 specify a universal taxonomy and a classification of the major types and the forms of emergence in multi-agent systems, from simple types of intentional and predictable emergence in machines to more complex forms of weak, multiple, and strong emergence. This paper briefly presents a taxonomy based upon five orders of emergent behavior with four suborders and briefly summarizes the author's continuing research in this area. Taxonomy is basically an equation to classify the emergence type. So the orders, there are five orders of taxonomy with four suborders. Type 1 emergence is in fact no emergence at all. Type 1 emergence is characterized by feedback that is only local to global, or there are no feedback from the global to local. Type 1 is further subdivided into Type 1a, in which the emergence is intentional. For example, a designed machine such as a clock, in which each component is specially designed to carry out a specific function. Type 1b emergence is distinguished by the interaction of many loosely coupled and unorganized but equal components. Type 2 emergence is primarily distinguished by feedback from the system to the components, which is top-down feedback from the global level to the local level. This is the form of emergence typically associated with multi-agent systems, wherein the interactions of many agents react to the global influences, yet at the local level give rise to patterns observable at the global level. Type 2a emergent behavior, the feedback from the global to the local is net negative, and so impose a constraint or moderating influence on the actions of the agent and generally results in a stable global system. In Type 2b emergence, feedback from the global to the local is net positive and typically result in rapid, often exponential, changes in the system and general instability. Type 3 emergent behavior combines the characteristics of Type 2a and Type 2b emergent behaviors. It describes systems that exhibit both net positive and net negative feedback. Type 4 evolutionary emergent behavior is distinguished by changes in the governing rule sets within the local entities, which is from a state space perspective. Each entity may, by various means, add or delete from its governing rule sets. So the taxonomy is basically an equation to classify the emergence type, which is equation 1. And for the case of a system composed of finite state automata, the assumption is that the component's state space is static. This makes a function of time as the states of the system vary in time. So the equation becomes the equation 2. Critical analysis. Will it really work? Maybe not. Because in the paper there is only a simple example to demonstrate how it works, but not proved it works. Have the author achieved the goal? I think the author's goal is to build a taxonomy for the EBS, but I think it's just a prototype that he built. So yes, he built a taxonomy prototype for the EBS, but it's not applicable, not yet. The main drawbacks of the paper, I think, is that there's no data or experiment to support the taxonomy equation to prove that it really works. Would it work under different conditions with other less constrained assumptions? First, not discussed in this paper is the effect of varying n, which is an important parameter in the equation. Second, equation 1 indicates that increasing n would require a corresponding increase in intensity of constraint if the desire were to decrease the number of states of the system. Equation 2 must be re-derived for the combining of states that occurs as entities, comprising a system from structures that affect the system. That would be all. Thank you for listening, and I am here to answer questions.